That was the most technical podcast I've ever done. I think that was one of my favorite conversations for sure. Hey, I'm Guillaume Verdon. Growing up, really, I was pursuing theories of everything. I want to understand the universe. Was a big fan of Feynman, Stephen Hawking growing up. And I was 7. I was like talking about subatomic particles. And
As all 7-year-olds do, right?
I guess I got swept up in the school of thought that was, a generalization of Wheeler's it from bit, which was the it from qubit program, seeking to unify theoretical physics through quantum information theory. So viewing everything in the universe as one big quantum computer running a certain program or self-simulation. We have proof of existence of a really kick-ass AI supercomputer that we're both using right now to talk to each other. It's our brains. That, I would argue, is a thermodynamic computer, right? Because there's master equations describing the chemical reaction networks in your brain of neurotransmitters hopping around. And so, if we're doing very similar physics, but with electrons sloshing around a circuit, then, there's a very much stronger chance that we could run a very similar program in a very similar fashion, arguably with even more energy efficient components because electrons are much lighter than big neurotransmitters.
This podcast is supported by Google.
Hi folks, Paige Bailey here from the Google DeepMind DevRel team. For our developers out there, we know there's a constant trade-off between model intelligence, speed, and cost. Gemini 2.5 Flash aims right at that challenge. It's got the speed you expect from Flash, but with upgraded reasoning power. And crucially, we've added controls, like setting thinking budgets, so you can decide how much reasoning to apply, optimizing for latency and costs. So try out Gemini 2.5 Flash at aistudio.google.com and let us know what you build.
Hey, I'm Guillaume Verdon. I'm the founder of Extropic, a company pioneering thermodynamic computing, a new form of computing for probabilistic inference using exotic stochastic physics of electrons. Formerly, I was working on quantum computing and machine learning at Alphabet, and I also happen to be the founder of a philosophical movement called Effective Accelerationism under the pseudonym Beff Jezos online. Happy to be here at MLST.
Hello, everyone. Welcome to Machine Learning Street Talk. I'm your host for today, Maxwell Ramstead. Very excited to be here. I'm subbing in for Tim Scarf, who unfortunately is down with a little bit of COVID. But I'm sure we'll have a really interesting conversation. It promises to be a super interesting conversation because we have a really awesome guest for today. Very excited to have Guillaume Verdon, also known as Beff Jezos on X and just generally online in the meme space. Very excited to have you, Gil. How are you doing?
Yeah, thanks for having me. Thanks to MLST for hosting, and it's great to talk to you again, Maxwell. I think this collaboration, at least for this conversation, has been a long time coming. So it's a great platform to do it, and let's get to it.
So you're a very interesting character, Gil. Like you're a fascinating researcher. I think you're a big presence like in the meme space as well. Do you want to tell us a little bit about yourself? Like tell the audience a little bit about your trajectory. How did you wind up being, the CEO of a thermodynamic hardware company and also, basically like a well-known, person in the meme space as well?
Yeah, I mean, it's been a long journey. I guess I've lived many lives. Growing up, really, I wanted to, I was pursuing theories of everything. I want to understand the universe as one does, and eventually leverage that knowledge to expand civilization to the stars. Originally, my plan was to become a theoretical physicist and work on quantum gravity and figure out some, exotic form of propulsion that would obviously, I thought that was the bottleneck for the expansion of civilization was the speed of propulsion. And so I went down that path, was a big fan of Feynman, Stephen Hawking growing up, and of
So this is a childhood project. Like since you were a wee boy,
Yeah.
you've dreamed of.
Yeah, no,
That's
I was
cool.
7. I was like, talking about subatomic particles and
As all 7-year-olds.
yeah,
do,
and I
right?
want to be a physicist. And I want to be. I used to call it astrophysicist. I didn't know what theoretical physicist was. But I want to be an astrophysicist. I want to work on, FTL travel and stuff like that. And over time, I did the career path for theoretical physics. I did math and physics in undergrad at McGill, and then I went to Waterloo, the Perimeter Institute, for theoretical physics. Met some of the greatest minds on Earth. They're really strong caliber. But what I realized going through theoretical physics was that the reductionist approach to physics was failing us, right? Originally I was like, okay,
Do
well,
you want to, just for the benefit of our audience, what do you mean by the reductionist
yeah,
approach, and
let's-
what do you think were the problems?
yeah, and I guess these two sides to my life now came from my reaction to realizing this failure. And the reductionist approach is kind of the traditional way we've done physics. It's kind of the very sort of rational, old school way to do things, which is like, oh, I want to have a model. Maybe it's an equation, it's some analytic model, and it has a few parameters. And I've reduced all of physics to a very simple model with few parameters, and ideally the least amount of parameters possible. Occam's razor principle. And these equations with these few parameters allow me to have predictive power over the world. And with this predictive power, I can steer the world. I can do things, right? I could predict and control it. And that's the goal of physics, is to have better models of the world. And what we realized was that, I was part of this, I guess I got swept up in this school of thought that was, a generalization of Wheeler's it from bit, which was the it from qubit program, which, was seeking to unify theoretical physics through quantum information theory, right? Viewing everything in the universe as one big quantum computer running a certain program or self-simulation. And that framework's actually a really useful kind of unifying framework to understand all sorts of systems. And people were studying sort of systems that, have some connections between quantum gravity and regular quantum mechanics in the context of holography. So, ADS CFT for those that are familiar. But really what I realized there was that even whether or not ADS CFT was going to work, it was clear that the complexism approach to physics was the way forward. The universe is very complex. Even beyond just quantum gravity, just looking at condensed matter systems, you can have equations describing the microscopics, but you can't predict the emergent properties, right? You actually have to apply an amount of computation that is similar to that of the universe to have a prediction of what happens at a larger scale, right? Not all equations you can renormalize, analytically. Renormalize means get an effective physics at a larger scale, at a more coarse-grained scale, right? That's how we go from different types of physics, from quantum field theory to quantum theory to statistical mechanics, and then eventually classical Newtonian mechanics, and then even beyond that we get to general relativity and so on. So clearly it was the way forward was to understand everything as a complex system, but that was a sort of ego death, because in a way, the human can't necessarily be the hero of the story. The model is no longer interpretable, right? If you have something like a deep learning system, back then we were looking at tensor networks, which are a different sort of parametric complex system that we use to model, let's say, condensed matter systems or quantum gravity systems. If you look at these systems, they're no longer interpretable, right? I could have these big networks, and they're just as opaque as the system that I was trying to predict. But with numerics and with a lot of compute, you're kind of not deferring agency, but you're leveraging a programmable parametric complex system to grok a complex system of nature for you. And in a way, it was like, okay, well, maybe I can't be the hero of the story. I won't be the one to figure out, the grand unifying theory of physics, but maybe I could build a computer or computer software that can understand the universe or chunks of the universe for us. And actually, the more I dug into it, it was clear that this was going to be the way forward, right? And
so basically building a digital brain to overcome the limitations of our fleshy brains.
Yeah, but even that's correct. But then, at the time we were studying, I came at it trying to understand quantum mechanical systems. So you had systems that have quantum complexity, and there you can show that actually classical representations will struggle to capture quantum correlations. So already, I came at it from a non-anthropomorphic form of intelligence. To me, intelligence was just I'm trying to learn compressed representations of systems through parametrized distributions, or in my case, it was parametrized wave functions and density matrices, right? Which is the more general form. So that actually got me into a field. Initially it was mostly numerics with tensor networks, but there was another institute I was part of at the University of Waterloo, which was the Institute for Quantum Computing, right? And there is very interesting because we had these controllable quantum systems, we had these control parameters, right? And it became clear to me that there was maybe a way to run these representations we were trying to learn of quantum systems that are parametric on a parametric programmable quantum system, right? And so now we could fight fire with fire, right? We can have parametric quantum complexity that's tunable to understand quantum complexity of our world, right? And that was actually my entry into artificial intelligence. And I wrote up some of the first algorithms for quantum neural networks. So that's what we called them. They have nothing to do with actual neurons. They're just parametrized quantum programs. But essentially, was one of the first quantum computer programmers, was the first user of Rigetti and so on, which was one of the first startups. But essentially that got me on the radar of Google, who then approached me and a team I built at Waterloo, an open source team, to go work at Google and build a product known as TensorFlow Quantum, which was a product focused on creating software that allows us to learn quantum mechanical representations of quantum mechanical systems in our world. And that was my entry into AI, which given that this is a technical podcast, I'm kind of going a bit deeper than I usually do, which is really nice in the backstory here. But over time, what I realized was that actually this sort of physics-based approach, right? Like if we have if we're trying to understand the physical world with representations, we want to have physics-informed representations or physics-inspired representations. Just like to understand a quantum mechanical system, I use a quantum neural network, and then the dual to that is if I want to run and learn and train these representations that are physics-inspired or physics-based, then I need a physics-based accelerator, right? That where that type of program kind of fits natively and can be executed as physics. And in my case, initially it was I want to understand quantum mechanical systems. I want to learn quantum physics-based programs, and I run them on quantum physics-based processors, right? And so
then I have a clarification question just for the benefit of the audience, because we have a very technical audience, but let's just make sure everyone follows. So what do you mean precisely by physics-based computing? So the question I ask because it might confuse some of our listeners. In some sense, all computing is physics-based, right? Like it's all shuffling around, electrons shuffling around in circuits and so on. What do you mean specifically by physics-based computing, and how would that differ from, the kind of commonsensical or classical notion?
Yeah, I mean, a quantum computer is a computer that leverages quantum mechanical evolutions as a resource, I would say. It's there's more formal definitions of what a quantum computer is, but a physics-based computer, I would say, of course, like every physical thing is embedded in the physical universe, so everything is physics-based. But it's true that it's kind of a continuum, right? Because you can have physics-inspired computers that are doing digital emulations of physics-inspired algorithms. So I would say that's physics-inspired. I would say a physics-based computer, at least for a quantum mechanical computer, is one where you have a sort of parameterized Schrodinger evolution that you control, and you can show that it has some unitarity. And then in our case, and we'll get to that, we're building physics-based stochastic computers or stochastic thermodynamic computers. So they're parameterized stochastic evolutions that we control. But in principle, you could try to emulate a quantum mechanical computer, emulate a stochastic computer digitally. Of course, in the case of a quantum mechanical computer, there's proven separations of complexity there, and there's experiments showing that you can't emulate them at scale. In our case, with stochastic computers, there's no complexity class separation. It's just kind of just orders of magnitude constant speed up or energy efficiency gain, which practically makes them intractable to emulate at scale, right? Not impossible though, of course. But yeah, so this journey, and feel free, if you have, do you have a better? I think you have a better definition of physics-based computers. I don't know if you want to go into it.
Well, no, it's consistent with what you were saying. I mean, I would, at a very high level, I would say that a physics-based computer is essentially a computer whose components exploit, the actual physical properties of the components in order to, perform computations more efficiently. So rather than use digital computation to simulate what, for example, is like a quantum phenomenon or a thermodynamic phenomenon, you actually use, the probability densities that these systems embody, for example, at equilibrium, and exploit those properties in computation. Would you agree with that as a broad definition? I mean, I know
that's
I'm not
for a
getting as
thermodynamic
technical
computer, right? But yeah, so there's different kind of physics and different kind of corresponding physics-based computers. Arguably, you can have one. You can have probabilistic or quantum photonic computers. Of course, you can have physics-based computers in all sorts of substrates. Technically, you could probably train a neural net from puddles of water, right? If you wanted, and that would still be a physics-based computer. So I think it's kind of a very broad community. I would say physics-based computing, if we include quantum computing and alternative computing, and there's all these archipelagos that don't necessarily talk to each other. And I think there could be more work in trying to unify the community, because there's a lot of tools that could cross-pollinate between these different substrates. But to get back to our main line here, which is how did I end up going from quantum to thermo? Well, I think going from being one of the first programmers of AI on quantum computers and seeing the field kind of evolve over several years. I mean, I was almost 8 years in quantum computing. It wasn't progressing as fast as I wanted, and I was seeing a sort of writing on the wall where actually to have a quantum mechanical computer, you try to keep the computer at perfect zero temperature, right? Zero entropy. So you're constantly pumping out entropy that is seeping into the system through noise, right? And that's quantum error correction and fault tolerance. And it turns out that most of your computation, most of your energy is going to be sunk into that pumping. So it's like an algorithmic form of refrigeration. And to me, it's like, okay, well, it's just like, if you have a fridge and you're trying to keep your freezer really cold, it's going to use up a lot of energy if the rest of the room is at room temperature, because that gradient of temperature is very difficult to maintain. And so it's like, okay, what if we had a hotter physics-based computer? Maybe it'd be much easier to maintain, just the first thought, right? And so what would that look like? Well, in the limit where, you let the noise seep in, things become mostly stochastic, and the quantumness kind of fades out. And we know this from sort of renormalization of physics. That's why we don't have to care so much about quantum physics day to day, because it gets washed out at larger scales, right? And things become...
Would you say that it's accurate to frame it this way? In classical computers, the scale of the fluctuations is dwarfed by the scale of the components of the system that you're considering. So you can basically ignore the noise for the most part, assuming that you cool the system appropriately. And in quantum computing, it's almost the other way around, where what you want to do is basically to engineer the scale of the fluctuations that are so big, basically, that you can kind of ignore them relative to the component size. Then, and this is just a an attempt at framing what you're doing. Feel free to disagree with this. And then in the thermodynamic regime, what you have is fluctuations that kind of coexist at the same scale as the components that the hardware is made out of.
Yeah, I mean, we're in Wimbledon weekend right now in London, and you don't have to understand the vibrations of the molecules at the molecular level in the tennis ball to be able to predict its trajectory, right? You kind of get a mean field sort of prediction, right? So that's Newtonian. At the quantum scale, it's more subtle because it's no longer probabilistic fluctuations. You're essentially, it becomes all purely quantum superpositions, right? And the ideal quantum computer has no probabilistic uncertainty. And in fact, when there is probabilistic uncertainty, that's when the quantum computer loses its quantum coherence. It becomes non-quantum, right? But we have a very similar problem with classical computers that I realized, which was, we use all this power to be, again, to have signal that's so strong relative to the jitter of electrons and the amplitude of that jitter, in order to maintain determinism, right? We want our transistors to be absolutely on or absolutely off because, we have a lot of transistors and we want the computer to be in a deterministic state that we have control over, right? Because humans like to be in control, right? When we're not in control, there's anxiety, right? I think we got to learn to let go. Just like I learned to, in a way, let go of control mentally by giving up the reductionist approach, which is like the human interpretable approach to physics. We have to sort of, just like we did with deep learning, we let go of software 1.0, imperative programming, and let gradient descent be a better programmer than you. And that was very humbling for some. Some are still trying to hang on for control, right? With ML interpretability research and all this AI safety research, and they still want to feel like they're in control or that they understand the complex system instead of kind of letting it do its thing and letting it figure out what's best, right? And that's also kind of my main gripe with the whole AI safetyist field. Of course, there should be some research in interpretability, but I just don't think they're going to go that far. But to close the loop here, I think we should also literally sort of loosen our grip on electrons and hardware, and that's what we do, right? Essentially, we go from having a very tight grip and yanking these signals around to kind of loosening our grip, letting there be fuzz, and kind of gently guiding the signals, right? And so we can...
So in some sense, you're kind of switching teams, right? So, in the more classical kind of way of thinking of this, what we're trying to do is to keep the noise at bay, right?
Yeah.
To make our systems as non-stochastic as possible.
Filter it, pump it out, pay the price.
That's right. But
right?
Exactly. What you're doing is saying, no, like harness it, right?
Yeah, but as we know, like from Maxwell's Demon, the classic fable, I don't know if we want to go through it right now, but, there, people can look it up. Maxwell's Demon shows you that knowledge comes at a cost, right? Like reducing entropy in a system, keeping something in a deterministic state always costs you energy. And so if every clock cycle we're trying to, prevent the classical or quantum computer from decaying to a naturally probabilistic and relaxed closer to thermal state, then we have to pay the price. We have to pay energy to maintain determinism and reduce entropy. Whereas a thermodynamic computer is not always at equilibrium, but we're dancing much closer to equilibrium, and it's much cheaper energetically to sit in those states and maintain those states, right?
Do you want to maybe just like walk us through, how are you actually like designing these things?
For a technical audience, I guess there are Markov chain Monte Carlo accelerators, right? And we support discrete variables, continuous variables, mixtures of the two. And essentially, we've found a way to harness natural stochastic physics of electrons in order to accelerate Markov chain Monte Carlo. And there's some subtleties on how we do that mapping, but you could just imagine we're embedding into the stochastic dynamics that are parametric and that we have control over those parameters. We're embedding our continuous or discrete variable MCMC into the dynamics of the electrons in the device, right? So it is partly analog, it is stochastic, but it's actually our most recent chip is a mixed signal chip. So we use digital classical components and sort of stochastic electronics, and the two have to interact just like in a Metropolis Hastings algorithm. You have some components of the algorithm that have some entropy, some proposals, and then you have some non-random parts, right? Like computing acceptance or rejection.
So I guess this helps you address the kind of paradoxical situation where, because I was just saying in some sense from the hardware's perspective, you're switching sides and joining the side of noise, but from the point of view of software development in the context of AI and machine learning, this has already happened, right? Like there's a kind of paradox in our current architectures where, as you just described it, we spend inordinate amounts of energy and effort pumping the noise out of the system, but then with sampling based methods, like we then reintroduce it through the software.
Yeah,
right?
and you could think of even a transformer. You have a softmax layer at the end. A transformer is a big probabilistic computer already. So we're running probabilistic software on this stack that was made for determinism. That's highly inefficient. And then now with test time compute, right? Thinking at test time, Monte Carlo tree search and all sorts of RL rollouts. That's a Monte Carlo algorithm, right? So that can be tree of thoughts. It could be discrete diffusion. It could be now even for content, there's diffusion models. Those are also, it's also a Markov chain, right? You're reversing a Markov chain there. So algorithms, the biggest workloads that are eating the world and consuming a ton of energy are actually probabilistic workloads. They are probabilistic graphical models. And so it's kind of funny, like there's just like I think it's just the community. There's kind of the new additions to machine learning that don't learn the fundamentals. It just goes straight to transformers and whatever's hot. And then I tell them we're building an accelerator for probabilistic graphical models, and they look at me like, "What are you talking about?" It's like, actually, you're running probabilistic graphical models all day, it's kind of funny that there's a gap there. But hopefully, I think coming on this podcast and hopefully getting more in the machine learning community to talk to each other, I think probabilistic ML hopefully will have a resurgence, and of course we're trying to stimulate that, right? Because what there's a coevolution. What evolves together fits together, right? And there's an evolution of hardware and algorithms, and we have as investors two of the authors of the transformer paper, and they say they kept telling us transformers are not sacred, right? They were what worked on the hardware we had at the time, which was Google TPUs, and the hope is that there's going to be new foundation models or new models that run more natively on probabilistic hardware that are really efficient on our hardware, and we're not just importing current day models, but hopefully by if you view the algorithmic landscape as having a certain fitness function of what in terms of performance you get, in terms of cost, but also it's induced by the current day hardware that's available at scale, right? And if you change that hardware substrate to a different substrate that has different preferences in terms of the structure of the algorithm that you're running, then you're changing the fitness landscape. And if you have a sudden shift in the fitness landscape, you have a sort of Cambrian explosion. You have this sort of high temperature phase of search, right, in the landscape, and that's hopefully what we're gonna cause, right? And that's very disruptive. So incumbents have all the reasons to be skeptical, but at the same time, it's funny that even the current sort of incumbent algorithms are converging towards sampling and more probabilistic algorithms, which wasn't obvious when we started the company in 2022, but that was the prediction, right? That there would be a sort of my joke is that we're kind of interpolating between kind of deterministic forward pass models and full EBMs, right? And you can view sort of diffusion models as an interpolation there.
But I mean, correct me if I'm wrong, but your view is that this is essentially an inevitable development of tech, right? Like you've talked about the thermal danger zone and kind of the inversion of this Moore's law into what you call Moore's wall. Do you want to kind of run us through the logic there?
Yeah, I mean, if I came from quantum computing there. If you if you try to scale up your system, you have noise seep in. So again, you're kind of you're going from the quantum zone of physics to the thermodynamic. You're kind of edging on it, and then if you're in the classical zone, but you try to get smaller, then you're getting in the thermal zone again, right? In terms of the physics, and then the jitter of electrons, because your transistors are so small, the fact that there's very few electrons, and the transistors are small, the jitter of all the electron population matters compared to the amplitude of the signal.
Right.
And then, typically we like to have our computers have an error rate of 10 to the minus 15, so that you can do many, many operations before there's an error. And then so that you don't actually have to run error correction, right? The only computers that usually run error correction are those that we send in space because of radiation, right? But, the reason we can't scale down deterministic computers is because of this thermal danger zone, and they're innovating in all sorts of ways. They're doing all sorts of weird fins and all sorts of weird designs that are sort of hardware level error correction. But
those are always going to be ad hoc in some sense, right? Because what you're going to run into is just the scale problem.
Yeah,
right? Like, as you miniaturize at some point, these wires are going to become. Yeah.
To use less power, you need to use less charge. That's not controversial. I mean, when you get to very little charge, the fact that charge is discrete gives you noise, period. Right? And so you're going to have to go thermodynamic at some point, right? And, at the end of the day, we have proof of existence of a really kick-ass AI supercomputer that we're both using right now to talk to each other. It's our brains. And that, I would argue, is a thermodynamic computer, right? Because there's master equations, right? Describing the chemical reaction networks in your brain of neurotransmitters hopping around, and you could just
operating really close to the Landauer limit as well, right?
Right, and so if we're doing very similar physics but with electrons sloshing around a circuit, then there's a very much stronger chance that we could run a very similar program in a very similar fashion, arguably with even more energy efficient components, because electrons are much lighter than big neurotransmitters. And so,
so basically what you have is like a programmable bowl, right?
Well,
like you can think of these chips as like a kind of programmable bowl. Do you want to maybe tell us how they're used for computation?
I think I think we started off in superconductors, and the reason we started in superconductors was because there's this beautiful theory in quantum computing actually called circuit quantum electrodynamics, where you go from here's my circuit and here's my Hamiltonian, right, directly from the circuit, and I think that should win a Nobel Prize or something someday. But that's basically how we engineer quantum mechanical systems to have certain desired physics, right? And the point there is that a Hamiltonian gives you a notion of energy, right, in the classical regime. And so we had a very direct way to go from, hey, I want this energy, here's how I design my circuit, right? And so that's where we started. Furthermore, it was the way to build the most macroscopic thermodynamic computer you can build. Any other companies with claims to build a much more macroscopic thermodynamic computer either did it digitally or emulated it, so it's not a real thermodynamic computer. But we had to super cool it because it's too big, right? And Boltzmann distribution is, as you go smaller, you have higher frequencies, you can go to higher temperature, and then we move to silicon. But to answer your question about energy-based models, you could view our chips as a time-dependent programmable energy function, right? And you have something akin to Langevin dynamics, more generally diffusion, in that landscape. And Langevin dynamics is happens to also be an MCMC algorithm, right? So there's a perfect match there between the algorithm that you can use for Bayesian inference for anything really, and the native physics of the chip, right? And so it's almost
That's so cool.
It's been there the whole time, right? And it's like we've been doing algorithms that were physics that we could literally implement, right? It's a literal analogy, and we're instantiating as an analog computer. It's that was too beautiful to not build it. So we did build it. Hopefully we could cut some B-roll. I brought some superconducting chips here. We'll do that later. But now, actually, I think the big breakthrough and the big challenge was to
That's it, eh?
move to silicon. Yeah, and
Wow.
getting programmable stochastic physics in silicon was a whole kind of order of magnitude more difficulty, and we had to really innovate in terms of understanding, stochastic mechanics of electrons in silicon, and we built our team for that. And essentially, we kind of reproduced some core primitives, namely the one we're talking about for now is the probabilistic bit, and the probabilistic bit you could think of as a double well system, and you can tune the tilt and so on. So if you have if you consider bouncy balls in this landscape, you can control how much time the bouncy balls spend in one well or another, and you can consider one well 0, the other well 1. So essentially you have a signal that's essentially dancing between 0 and 1, right? And you can control how much time it spends in 0 and 1, and so that's like a fractional bit, right? So going back to what we were saying earlier about coming from qubit, we school of thought, we basically made p-bit from it, and it initially was superconducting materials, but now we've done p-bits in silicon and achieved really, really high energy efficiencies. Our p-bits can generate controllable bits of entropy with only a few hundreds of attojoules. And we've actually, as of recently, submitted our results for peer review, and we're going to put them on archive, probably timed with some other announcements in the coming months. But it's really exciting
That's so
time.
cool.
And again, this was a concept for a very long time, and it was a big risk for me. Initially when I left theoretical physics and went all in on quantum machine learning, everybody told me, like, really, you're going to be a quantum machine learning lead at Google, and everybody was doubting me. And then I became kind of well known, and then I eventually led a team. I led quantum machine learning at Alphabet X, and then I quit all that. I quit quantum computing, quantum machine learning, and it's like I'm going to take even more risk. I'm going to build a whole new paradigm of computing from scratch, from the concept up. And everybody thought that was crazy. And now we're here. Now we've made a lot of progress, and now we're scaling, right? And because there's nothing stopping us from scaling at this point, because we've de-risked the manufacturing as well, which is usually not something academics think about. But if you're a startup and you have to scale or die, eat the world or die, you have to kill every risk possible. So, we are looking to scale to millions of degrees of freedom next year, and I think we're gonna hit it. So
that's really exciting. So your first chip, right, had 3 p-bits.
Yeah.
And the latest has about 300 degrees of freedom.
Yeah,
correct. And
they're not all
now
p-bits, but
now you're aiming.
We'll get to that someday. Yeah.
Right. And now and millions of degrees of freedom.
Yeah.
Next year.
Yeah.
That's very cool. So help me understand the layout, the general space here. So, I mean, presumably, you don't think that this is or do you? Do you think this is a wholesale replacement for the current stack, or do you see because I could see a world where you interface, you use thermodynamic compute when it's relevant, but you mesh this with digital and quantum at the appropriate junctures, so that you get what you really get is a multi-scale stack where each hardware bit is specialized for the kinds of computations that run natively on that kind of hardware. Which out of the
Yeah, absolutely. I mean, if you're I think there was some work from Max Tegmark on correspondences between sort of the information bottleneck principle and sort of downsampling and the hierarchy and machine learning and the renormalization group, right? So in physics, you go, if you're trying to learn from quantum mechanics and you downsample, you get statistical mechanics, you downsample, you get to Newtonian mechanics. You can imagine if I had a God neural network that just compressed all the information in a certain region of space, which is actually the thought experiment that got me into quantum machine learning. I was trying to understand black holes as a machine learning system. But let's see, you created that system, then you can imagine the first few layers are quantum, and then some layers are probabilistic, and later they're deterministic. Just like as you distill distill the information. You don't need that sort of, initially you need some quantum complexity, later you need some entropy, and then later you just need to do some classical, coordinate transformations, right? And they all work together. But in a more practical workflow, yeah, I mean, very often, whether you're doing simulations of stochastic differential equations, you're trying to simulate a physical system, whether you're doing some sort of discrete or continuous diffusion, there's very often there's a classical function, often differentiable program that determines sort of some probability distribution that you want to sample from, whether it's in latent space or for these transitions and the denoising. So the two work together. You don't necessarily need entropy everywhere in your graph all at once, right?
Right.
In principle, you could use a probabilistic computer for deterministic operations, but it's not going to be the best at that, right? In the low precision regime, right, you could think of p bits as literal fractional bits, so you can get into the fractional bit precision work, and so that can be interesting, but not everything is well suited for that low precision. I do think quantum computers will have some applications, but again, they would be supplements for just quantum mechanical systems, to understand quantum mechanical systems as a supplement to probabilistic and classical computers. But I would say that most things are, would be well covered by probabilistic and deterministic representations running on probabilistic or thermodynamic and deterministic computers. Yeah.
So currently the superconducting chips require a lot of cooling, right? You need to get them around 1 Kelvin. Is that the case?
Yeah, I mean, depending on the material, you can be a few hundred millikelvin, or you can get to a few Kelvin. A few Kelvin, usually using niobium. I think that you don't need as big of a fridge. For us, it was an interesting sort of experiment, and we have a bunch of results there. We have a paper coming in the coming months. Essentially, it's as efficient as we could imagine building a thermodynamic computer. And again, it was just to get people to imagine, hey, actually, or realize rather, hey, actually, there's forms of computing that are far more energy efficient by like an unfathomable amount of orders of magnitude, far more efficient than digital computers, right?
Right.
And
Because I'm just doing some back of the napkin. Because so you guys target 1,000 to 100,000 x energy efficiency gains at the chip level. And what I was wondering is, how does that discount against the cryogenic energy costs? Like, how does that factor into your efficiency calculations?
So any sort of anything from those results were, and we put the asterisk there, like that's just the chip, and in general, you'd have the thought experiment was, if you scaled a very large network of superconducting chips to football field sized, and you had a ginormous dilution fridge, right? Again, it's like the big energy cost is maintaining that boundary, right, with the outside world. If you had a ginormous dilution fridge and you had millions and millions of p-bits and superconductors, you'd have the most energy efficient probabilistic computer, right? Is that practical? Probably not. Should a startup be doing it? Probably not either. Could a government do it in some sort of crazy moonshot? Maybe. So we're kind of just going to put the idea out there for academia, national labs, and whatnot to pick it up. I think for us, it was also just a great learning platform. Superconductors are ironically pretty accessible. A bunch of universities have fabs where you can experiment with them. So for us, it was kind of like, hey, we're going to want a community of people working on thermodynamic computing and experimenting with new primitives and showcasing new algorithms. So we're going to put out that work into academia. But for us, the product is, again, the silicon chips, which, we could have decided to run them in cryo CMOS, but we ended up deciding to go for room temperature. Of course, a thermodynamic computer at lower temperature consumes less energy, right? Of course, you're assuming you're maintaining the bath at that temperature, but then you have the costs of the cooling, right?
Right.
So, if you had a von Neumann probe thermodynamic computer, maybe you could run much cooler, right? If it's going to go and enter in interstellar space, it's not going to encounter that much heat. And so maybe we'd modify the design for that. But that's, much problem for in the far future.
And then coming back to impacts on the AI industry, I mean, EBMs have been around, energy-based models, right, have been around for a long time. Would you say that this is really the key to unlocking their potential? Because up until now, they've been basically limited by their inefficient sampling, right? So would you say that this is really like the technology that we need to really do the EBM thing seriously?
I think modern neural networks are just mean approximations of EBMs, right? Like neural networks came from EBMs.
Right.
The 2024 Nobel Prize was, and backprop came from looking at mean field of EBMs. So to us, we're just, creating the hardware for the ancestors to neural networks, and they're kind of a superset, right? You could just take averages and get deterministic operations. And so, our hope is, people think of going more probabilistic with their algorithms now that sampling is far more energy efficient and far faster. But because we've been stuck with deterministic computers, people have just tried to avoid, using primitives that have, they would just represent distributions by their moments, right? And they would use, exponential families where you don't need too many moments, such as Gaussians, right? Because you could just represent them as matrices and vectors, and matrices and vectors can fit on a GPU really well, right? And you could do some transformations there. So there's been a bias in algorithms towards what runs well on today's hardware, and hopefully with thermodynamic computers it changes that. And so we're trying to get people interested in the space and to start imagining what they would do with multi-million.
This is how you break free of the.
Go ahead.
Well, this is how you break free of the vicious cycle that we're stuck in, right?
Yeah,
now,
we're stuck in
like a hardware stack that works in a certain way.
Yep.
We optimize our software for that, then we build bigger hardware, and know, so this is how we break free from.
Yeah, that. But I think we're gonna break free one way or another, because frankly, even if you just do a back of the envelope calculation, right now we're gonna run out of power trying to scale AI. We can't even, if everybody were to use like an agentic, big model, ChatGPT or Grok model, we'd run out of power in the United States. You can't deploy it to everyone. You can't have everyone using it like with high intensity right now. We're going to run out of power. And then that's not even getting into sort of video models, world models, which are going to be necessary for embodied intelligence. At that point, if you try to scale it to the planet, we're going to run out. Even if we produce the power, let's say there was some moonshot, and let's say we even figured out nuclear fusion, right? Let's say we just did that and we scaled that very quickly. We'd run out of, or, we're going to generate more, we're going to double or triple the amount of heat being radiated by the Earth, right? So we're going to literally cook ourselves to death, right? We're literally cooked, okay? And so something has to change at the hardware layer. We can't scale with the current hardware. And so people thinking we're just going to scale transformers and get to the moon and scale intelligence to the whole planet, they're just flat out wrong, right? It's like provably wrong.
When people say, hey, to scale up intelligence, we need to start building nuclear power plants, I always think, well, like I run on a glass of water and a banana, maybe a coffee in the morning, right?
Yep.
Like certainly this is not like a naturalistic way to think about how intelligence scales, right?
Because you're a thermodynamic computer, right?
That's right.
That's the thesis. But you can imagine, right? Like just taking our current design and scaling it to a wafer, you would have about 1.5 billion p bits, which you could think of as neurons, and about 20 billion parameters per wafer, and then you could do multi-layered programs of those, and that would run on not 20 kilowatts, which is what a current wafer scale system would run on, or more, maybe 100. It's 20 watts, right? Which is like our brain, right?
That's crazy.
And then if you have 100,
crazy.
or you have a few 100 billion parameter model running on 20 watts, then we're in the brain. We're in the same ballpark as the brain. Not quite. It might be like within 10x, but that's still much better than where we are, which is like 100 million x, right? And so that's where we're going. And again, it's not to us, it's far less crazy than quantum computing. There is no like quantum computer in nature that has very high quantum coherence, and we have exquisite control and very high quantum complexity. All systems decohere. We have, multiple billion thermodynamic computers out there in the wild, and they work pretty well. So we're just trying to tap into the same physics. We're not obsessed with sort of biomimicry. We don't call ourselves neuromorphic computing. We're just doing, again, approximate probabilistic inference as a service, but in hardware, in physics. And to us, that's kind of the parent workload of most of AI. And actually, it's not just for AI, it's for broader computing, right? There's simulation, optimization, and statistical inference, science at large can use this. So it's not just for Gen AI, right? We're not just riding the current wave. Yeah.
I have the pleasure of interviewing not one but two people
Sure.
today.
Yeah, I'll switch
like
hats.
I've got your exactly. We've got your alter ego on the call as well. So I guess to kind of frame up the transition to discuss, because for the audience, Gil, or rather aka Beff Jezos, is the founder of a philosophical movement called Effective Accelerationism, which originated as a kind of counterpoint to effective altruism, and I really want to get into the details there. But I guess to kind of set things up, like looking 10 to 20 years out, like how do you envision the future? And what role does acceleration play in your vision for the future?
Yeah, I mean, 10 to 20 years. I think we'll have embodied intelligence. I think thermodynamic computers will be pretty ubiquitous. They're going to be what runs embodied intelligence. We're going to have greater intelligence density in all our devices. We're going to have personalized, always on online learning intelligence. And so, my goal is for everyone to own and control the extension of their cognition. Because that is important to maintain
democratizing intelligence.
Not just truly, because democratizing access. It's like, hey, I give you access to the one God model that amortizes its learnings across the fleet. Now you're all mind merged with my Borg mind. Congratulations, you've been assimilated. That's not democracy, right? If you have control over its constitutional prompts, you're essentially controlling people by proxy and their thoughts and their will and their actions, right? If you control it's not just, it used to be people control people's access to information and they steer them indirectly, but now it's going to be directly controlling the model that's an extension of their cognition or their thought partner. And then that's much deeper and more subversive control. And so to me, I think that was the big existential risk that I was most worried about, was the sort of precedent of people vying for control and vying for power, right? Over people.
Right.
And that's why I've been pushing for decentralized AI, and I've been pushing for sort of avoiding sort of overregulation of AI that would cause red tape inflation and would mostly serve the incumbents and would cause a centralization of AI power. I mean, someday I would imagine 10, 20 years out, hopefully, we're wearing some Neuralinks, our whole skull is some Neuralink that is the thermodynamic computer that's an extension of our cognition, and it's as powerful, or it's not more powerful than your brain, and you have a full merge there. I think something more plausible on a 10-year time scale is a sort of soft merge, right? I mean, you're the active inference expert here, but if you have the same Markov blanket, right, you have the same perception and action states, right? So let's say I had an agent, let's say my glasses were very smart and they were always on, always listening, and I have an earpiece. I could have sort of subconscious thinking, almost. It could just perceive things and suggest actions. So we're sharing perception and we're sharing actions through my body. We are the same agent, right? So that is a form of merge, and you don't need a neural interface for that, right? And maybe we even have a way to communicate non-verbally, or just like friends that hang out a lot have a prior of each other's behavior, or their behavior conditioned on the world states, and then they don't need as many bits of information to to adjust to a new setting. And so that's kind of a more plausible way. I think the soft merge is going to come first, but I think it's going to keep escalating, and then we're going to go towards a harder merge, right? A hardware merge.
So that's a very compelling vision for the future. It's very techno-futurist. I love it.
Yeah.
Do you want to give me the elevator pitch for EAC, effective accelerationism? So, because I think these are all related. I think this sets you up nicely to kind of just, present the kind of core idea. So,
yeah, I mean, really, EAC is a sort of meta culture. It's kind of, I call it like a cultural hyperparameter prescription, if you will. And it's one where we're trying to maximize growth of civilization as measured by our free energy production and consumption, aka the Kardashev scale. The Kardashev scale is a log scale tracking how much free energy is consumed and produced. And really, it comes from this sort of realization as I was studying stochastic thermodynamics in preparation for founding Extropic. I realized that, there was this sort of generalization of Darwinian selection, which is, thermodynamic selection, where each bit, you go from selfish genes to selfish memes to selfish bits. Every bit of information specifying configurations of matter is fighting for its existence in the future. And the selection pressure on those bits of information are whether or not they confer their host organisms an ability to understand their environment, predict the future, capture free energy, use it strategically, and grow. But really, the master, metric is like how much, if I change this parameter, this value, and I let time evolve, how much free energy has the system dissipated through its trajectory, right, over time, right? And the theorems of stochastic thermodynamics tell us that actually trajectories of the system that have basically consume more free energy are exponentially more likely, right? And so that's how you have this sort of pruning of branches that that consume less free energy. And so it's like, okay, well this is the golden metric of sort of selection pressure on the space of bits. And so I will design the highest fitness selfish meme that is EAC, which is figure out what is optimal for growth and do it. And so by construction, it should be the most viral thing, and it will persist.
Right.
and surprise.
The assumption there is basically the alternative is basically growth or death, is what you're suggesting, right?
Yeah, we have the saying "accelerate or die." I mean, it sounds dramatic, but it's meant to sound dramatic, but it's also reality. It's either you align yourself with growth and you are part of it, right? So whether you adopt your culture towards growth, and then you're part of the growth and you benefit, or you don't, and then you get outgrown. And whether it's at a national level, right, with your policies, right? Again, EU versus US. US is obsessed with growth to some extent, and we've seen a sort of bifurcation, in the GDPs and so on. So at a policy level, at a cultural level, even at an organization level, right? If a company is not obsessed with growth, eventually it just gets disrupted by one that outgrows them and then has more resources to outcompete them, right? And so I think the point is that essentially, if people are open-minded about new technologies and in general and lean in, they will be they will be selected for, and the people that are skeptical, push them away, shun them away, want to go back to the cave, get selected out. And so even from an empathetic argument standpoint, trying to popularize acceleration, like awareness that actually this is how the world works. I'm sorry to break it to you. You either embrace the acceleration or you get selected out. It's also kind of like, hey, if you care about yourself and your tribe, your company, whatever, you should lean in rather than lean out, and don't listen to the people telling you, fear mongering you. They're actually very often doing so out of self-interest, and it's an actual form. I view spreading deceleration as a form of warfare that is psychological. In fact, that's how I view it, and that's why I've been such a warrior online against the decel mindset. I just don't see a scenario where being decel is beneficial to the host, and in fact, it's just exploiting this gap in understanding of how the world works to destroy competition, right? And I mean, there's a lot of this in nature and in general in human dynamics. People kind of sabotage each other to outcompete each other.
See, I've been thinking about this a lot. My good friend and colleague Axel Constant actually, and I have a long-standing debate as to whether ethics, morality, and this kind of thing can be reduced to free energy minimization at the end of the day. And I think it's a kind of difficult question because thermodynamics, right, describes all mesoscale objects, right? So basically any configuration whatsoever will be, will be minimizing free energy in this fashion, right? Like, seeking to find pockets of free energy and dissipating it as efficiently as possible. I guess my worry is that things that grow without bounds. I mean, in the biological case, you have like cancer, for example. So I guess, like, what's the role of constraints in the maximization of entropy when we're kind of designing the social system? Because surely, things like, dictatorships, fascist autocracies, those also minimize free energy. And you might even think,
they're local. They're a local optimum, right? They're not a global, right? Just like a cancer is like it kills the hosts, and that's suboptimal on a sufficient time scale. Again, it's not an instantaneous free energy dissipation, right? It's basically infinite time horizon, right? And so actually blowing up the planet does, burn up a bunch of free energy, but in the long term, you actually it's the same reason life exists. It's much better to sort of conserve and strategically use free energy to secure more free energy and keep growing and have some order rather than just like burn all in one go and have chaos, right? And thermalize in one go, right? Again, that's why we have life. That's why we're not at equilibrium, right? We're not just burning up all our fuel and just dying immediately, because as intelligent beings, we burn way more energy by being this sort of partially somewhat coherent system that has predictive power of its environment, and we're kind of this energy seeking fire, right? And I mean, but this is, I would argue that IAC is also, it's kind of a call to kind of popularizing complexism and complex systems thinking and the free energy principle at large. And we have to think through this lens about all systems in society, from policymaking to technology to innovation to basically everything, economics. And it's a different way of thinking, one that is somewhat scary. Again, it's going from reductionism and rationalism to sort of complexism and post-rationalism, and we don't have as much control and interpretability. We don't understand the world as well, right? We kind of have to, pardon my French, but fuck around and find out, the FAFO algorithm, right? Like, but really it's kind of like exploration and discovery, right? You kind of a priority don't know what's optimal, right? And in startups, you kind of learn this, you have to actually go out in the market and try stuff. Sometimes your model-based prior can't do that well because the system is too complex to have a model that has good predictive power. You actually have to be in a sort of open loop. I would say that hopefully there's kind of a renaissance, and these ideas become more popular in all sorts of fields of science. Clearly it's eaten the software world, and we're trying to make this sort of school of thought eat the hardware world. And I think we will do it. But again, most fields of study could be revolutionized by sort of thinking through the lens of complex self-adaptive systems and the free energy principle.
So, I mean, you've described EAC as a kind of hyperstitious meme. Do you wanna say a few words about what that means?
Yeah, I mean, because again, you're the active inference expert. In active inference, you have perception and action, right? You can update based on your input sensory information, you can update your model of the world. So you're minimizing divergence of your model of your own internal model to the statistics of the world. But then the dual of that is taking actions in the world to minimize divergence between the world and your predictive model of it, right? And in a way, we're just naturally biased towards, in a way that the car goes where the eyes look, right, when you're driving.
Right.
And if we look at very negative outcomes and we're obsessed with them, we will drive whatever system we're thinking about towards those negative outcomes. An example of this, an example slightly controversial, is bioweapons research, and for example, COVID. Right? I would say that COVID was an accident from bioweapons research. It was probably defensive, and we were trying to explore what would be a really bad scenario. What if we had this mutation and this mutation would combine, and it would be a really bad virus? And then they start experimenting and designing in that neighborhood of virus subspaces that would have never occurred naturally, right? Just from evolution. But because we were exploring that subspace of bad things, because we're obsessed with it, we made it happen, right? And so, to me, it's like, if we're optimistic about the future, we tend to steer things towards that optimistic outcome. As a startup founder, if you're not optimistic about your startup, statistically you are screwed, right? Because
from the active inference point of view, every action begins with a false belief, right? So first you believe that you're moving, and then you reduce the prediction error in the direction of action, right? So
exactly.
I find this extremely compelling. I mean, one of the things I find most inspiring about EAC is that you're trying to present a radically optimistic meme for the future. And I think, there's so much, not just AI doomerism, but there's so much doom and gloom going around that just from the point of view of neurobiology, we need these kind of almost seemingly delusionally optimistic beliefs to get off the ground anyway.
Yeah.
Right.
I mean, you could think of the mimetic sphere as a meta cortex, right? It's a biological supercomputer. And EAC, we're just trying to do active inference towards better futures, right? So we're spreading this meme of optimistic futures, and it actually does steer the world. And, it's been 3 years now, and it has steered policies throughout the world towards, going for these moonshots and resurgence of, exploration of nuclear energy, to climb the Kardashev scale, deregulation of AI, widespread embrace of AI, companies being far more aggressive in their exploration of it. Overall.
So how do we spread it?
Yeah.
How do we spread EAC? I guess my question is kind of motivated. I think most of the very visible EAC figures, Andreessen, Musk and company, they tend to be, libertarian, right wing associated. If we
that
want
happened
EAC
after
to
the
really
fact,
be
right? So I would say, Gary Tan is rather on the left, and initially it was very apolitical. I would consider myself still a centrist, and kind of not hitting
Well, how do we get the abundance bros to join?
I think it's already happening.
I think
I think that was a reaction to EAC in kind of the techno optimist. You kind of end up getting clustered with one party in the U.S. In other countries it might be different, but there needed to be a actual techno progressive, let's say, versus techno regressive, cluster on the left. It's not clear that faction is kind of the dominant faction of the Democrats. I really hope it becomes that. Again, EAC is kind of like an RL algorithm. It's not clear what the optimal policy is.
Right.
I think a few years ago I was seeing a sort of convergence towards a lot of top-down control, a lot of top-down power.
Yeah.
And I think the optimal is always balance. You need some top-down control, but you also need sort of bottom-up self-organization. If you
That's
have
how the brain works, right?
exactly
Like
right,
you have a little bit of centralization, but not all that much centralization, right?
exactly right, and I think like absolute total libertarianism, it can work. It's just in the era of sort of unconventional warfare, complex systems also get adversarially steered, right? Whether it's free markets, they get gamed, or mimetic markets, right? There's psychological operations, and so on and so forth, dating markets, um, and so I think some balance of top down and bottom up is the ideal. Is it more like the U.S. or is it more like China or it's something in between? I guess we have to figure out, but that should
Well, that
be
segues perfectly into my next
yeah.
question. So, I mean, for you, this isn't just like a philosophical thing. This is like of geopolitical, geostrategic significance, right? Like this is important for the future of like, democracy as we understand it.
Yeah, I would say that our failure to view the world through as a complex self-adaptive system and still thinking in kind of the classical view of like, hey, I have a first order model of what's happening and I'm going to do a first order correction, right? And it's easy to convince a crowd of that, and politicians get elected on such platforms, but then they don't think of the higher order effects of their policies, right? And instead of thinking at it from a complex systems steering standpoint.
Mm,
And whereas I think our adversaries of the West understand the complex systems approach, and they tend to steer us in directions that lead to our detriment. And to me, it was like, okay, how do you fight a multi-dimensional war, where
mm,
there's like invisible sabotage of every complex system that can be steered adiabatically in nefarious directions, and if it's slow enough, then it's kind of above the infrared temporal cutoff that politicians give a shit about, which is 4 years, right? So if you're steering the United
right.
States or the West on a 20 to 40-year time scale, you could win a very long war, and we don't even find the pattern because we're too busy. Again, there's a sort of time scale separation here, similar to
Mm,
what happens in thermodynamic computing and thermodynamic physics. But essentially, we're so preoccupied with the dynamics that occur on small time scales, the day to day, that we kind of ignore the long trends, and those get sort of hacked, right? We slowly boil the frog. It doesn't
mm.
realize it. And
So
so,
in listening to you talk, it occurs to me that like there's a beautiful coherence to your approach generally, right? Because what you're doing both at the hardware level and at the level of your philosophical project is essentially kind of moving us away from hard, rigid programming from the
yes.
outside towards a kind of organic, adaptive, thermodynamic driven kind of learning and exploration of possibility space.
Yes, yes. I mean, again, it came from my own journey trying to understand physics and kind of discovering differentiable programming, and seeing that as the way forward for everything, right? And really, some of the prescriptions of EAC are to maintain variance and constantly explore across any parameter space, whether it's culture, aesthetics, policy, technology, etc. And one of the reasons is that according to Fisher's theories on evolution, the speed at which you can traverse a landscape, of course, it depends on the gradient, but also depends on the variance, right? Evolutionary search
Mm,
depends on variance, because the more you fuck around, the more you find out, right? And so your rate of learning is faster, and your rate of adaptation is faster. And to me, that seemed like the main advantage of the United States is that the United States is very high variance, right? They have high
mm,
variance individuals and they have high variance outcomes. And so I view the United States as a sort of high temperature search algorithm, and they're always first to. And I'm not American yet officially, but someday I will. That's my goal. But you know they're first to figure things out because they're always searching in very high variance. I view it as I view sort of innovation as a diffusion process in some landscape, and they're in very high noise regime, so they don't get stuck in local optima. right? Whereas, I would say China is more kind of like the low temperature sampler. They're kind of the optimizer at the end. They're doing the gradient descent, right? Once there's consensus, right? Once there's a clear gradient of direction of improvement, right? It's easy to convince a committee at that point, and then you can just execute top-down control with a lot of conviction. And so they beat us in the final stretch when sort of, you have it's kind of like Bayesian inference. You go from a unsharp prior to a sharper posterior on what's the optimal thing, right? It's like annealing, right? And so essentially China beats us at squeezing the end again, because they're fully kind of, they have a lot more top-down control power and a lot more coherence there. So I see this sort of we're kind of like a parallel tempering algorithm between the United States, the high temperature search and discovering things first, and then they don't, the optimizing and improving the technologies and scaling the manufacturing, they're not necessarily the best. And then China
then
squeezes the last bit.
How do we avoid catastrophic outcomes in that because you've been pretty dismissive about, like, P doom and doomerism generally. So how do we allow the kind of meta search to happen, but in a way that doesn't lead to a catastrophic, like, technological outcomes, or because I can also see some kind of tension between on the one hand this kind of open project, and on the other hand, like, the participation of, like, proprietary closed corporate groups. Like,
yeah, I guess, for me, P90 1984 was higher than P doom from AI, right? And so I think to me, I think China is like the ultimate monopolistic company, right? There's basically one set of executives for all the companies. They're acting like a conglomerate, and they throw their weight around to crush American smaller companies. And so, I would say that one thing about IAC is that we're kind of anti-monopolistic, because, again, monopolies tend to be suboptimal. Again, if you have choices of hyperparameters that are over-concentrated, you're not exploring anymore. And
we see that sort of motivates my question, and my worry is that, like, very authoritarian forms of government where we impose kind of like, ethnic or cultural homogeneity, like, those are very good at minimizing free energy, right? If you and I are exactly alike because there's, like, a top-down imposition of sameness, right, then that minimizes free energy super well.
Locally,
like, if we're all the
right?
same,
It's like,
right.
Well, if your energy term has, like, if you want to agree with your neighbor and so on, have no frustration, then of course, like, that's a local optimum. But as we know, like, what we're arguing for is embracing variance, right? Embracing different culture, having different bets, right? Like, even it could be culture, genetics. It could be ways to even train your ML models, right? I would say that actually we've had
same response to the cancer thing, right? Like, you're not worried about the push towards boundless growth leading to cancer type formations, because it's not a global optimum, it's a local optimum.
Yeah, that's right. I want to go on a slight tangent here that I think, like, for example, there's been some centralization in AI research labs, even though there's like 4 or 5 players that matter. They kind of churn. I mean, it's kind of been a meme recently that researchers, they kind of all slosh around and they all churn between each other. So they're all kind of equilibrating in terms of beliefs, right? Because you have exchange of particles of researchers between the labs. And you could see that, like, the American research labs all converge to similar amounts of performance at similar compute. And then, China with DeepSeek was exploring a whole different region of hyperparameter space due to its export control constraints, and then showed us that over-concentrating our bets in hyperparameter space has risks, because we're stuck in a local optimum, and there might be a better non-local global optimum, right? And that we're missing. And so, again, it's just been our push for variance there, in order to always be exploring. I think it's really important. I think it's really, I think basically there's also been a reaction to sort of Yeah, it's hard to explain. It's kind of like the same pattern that happens, in Western governments and late stage corporations,
Mm,
in large bureaucracies. There's a sort of cover your ass sort of mentality and culture, and decision by committee. And so it tends to be variance reducing, right, or variance killing, and taking
and
sort
that's sort
of,
of my worry. And
yeah,
in addition, I guess we're sort of in the same kind of situation as like a gradient descent learner, where like how are we supposed to know that we're not stuck in a local optimum, right? Like, because
yeah,
to us, like we might think, hey, like this is actually, this looks pretty optimal, but there's no kind of God's eye view that could tell us that
yeah.
actually we're just stuck in a
But
local.
that's why, as long as you don't kill variance completely, and you keep some explore, you're not just purely exploiting, and you keep open-mindedness, then you're always kind of, spending some resources still exploring, and
Mm,
and potentially finding a new better way to do things. Just like, I think, some people, at first thought our bet was ludicrous, and we shouldn't have raised VC funding. It's like, really, there's trillions of dollars of capital riding on the current paradigm, and you don't want a startup to raise a few tens of millions to take a bet that would be completely disruptive to everything, to this whole multi-trillion-dollar bet, right? And now
mm,
the tune is changing a lot, because people that are planning these $500 billion build outs want to know if a technology that's 1,000x better is around the corner, and could render some of their build outs maybe miscalibrated, right, in terms of the ratio of
right.
energy to compute and density, right? Again, I don't think, I think thermodynamic computing is gonna work in tandem with GPUs or TPUs or whatever, neural processing units. I think, it's going to take quite a while for models to be fully ported to thermodynamic computers. So for the foreseeable future, I think these buildouts are safe, and you could just have thermodynamic computing as an add-on. And
Gil, it's been a real pleasure to discuss these issues with you.
pleasure as always.
So how do we stay abreast of what is going on at Extropic? Do you
Yeah.
have any kind of closing message for us?
Yeah, well, so, stay tuned in the coming weeks and months. For those that are interested in trying out thermodynamic computing, in the coming weeks, we're going to give access to the first users to our systems, so you could test it yourself. It's mostly going to be private alpha in the early days. Again, we can't handle that many users. We don't have that many chips. But the technology is here. It's very real, and you can kick the tires. And stay tuned for some scientific papers, some open source software that we're going to put out. And I would say, start reading more probabilistic machine learning papers if you're a grad student interested in the area. Start reading about EBMs, and various textbooks. And stay tuned for more announcements from Extropic towards the end of the summer and this fall.
Well, for Machine Learning Street Talk, I'm Maxwell Ramstead. We're signing off, and thanks again, Gil. This was awesome.
Thanks, Max.
Yeah, and fascinating. Like really, really cool stuff.
Awesome.